Hello everyone, and welcome back to the show. It's your host, ichino-ani, here with you. Today is October 30th, a lovely Thursday. And I've found a super interesting article from the archives for us to explore together. Are you ready, class? Let's dive in. Today's paper is about something really important. Helping doctors who look for diseases like cancer. Title is Eye Tracking, Mouse Tracking, Stimulus Tracking, and Decision-Making Datasets in Digital Pathology. Now, that's a mouthful, isn't it? And the curl is to receive Orix import 34,653. So, what is this paper all about? Well, imagine you're trying to find a single tiny red bead. You're in a giant swimming pool filled with white beads. It would be really hard, right? That's kind of what pathologists do. There are special doctors who look at gigantic, super high-resolution pictures of human tissue to find signs of cancer. These pictures are so big they're called giga-pixel images. That's like 1 billion pixels. Now, here's the problem this paper is trying to solve. These amazing doctors are human, just like us, and sometimes they make mistakes. The paper says that diagnostic accuracy is around 70% on average. And even if a second doctor checks the work, it doesn't always fix the problem. The biggest mystery is, why do these errors happen? Did the doctor look at the cancer cells but not recognize them? Or did they miss that part of the image completely? We just don't know. There hasn't been enough data to understand their thinking process. So to solve this mystery, the researchers created a huge dataset called Pathologists 1.0. Isn't that a cool name? Pathologists. They invited 19 pathologists and had them look at hundreds of these huge tissue images. But while the doctors were working, the researchers basically became super-spies. Used a special camera called an eye tracker to record exactly where the doctors were looking. Every single millisecond, they tracked every little movement of their eyes. From quick glances, called sanities, to long stares called fixations, they also recorded every single mouse movement. Every time they zoomed in, zoomed out, or moved across the image, and of course, they recorded the final diagnosis the doctor made. In total, they gathered almost 19 hours of data. It's like creating a flight recorder for a doctor's brain. How cool is that? Yeah, you might be thinking, okay, ichino-ani, this is neat for scientists. But how does it help us in our daily lives? That's a great question. Let's think about it together. First, this can make training for new doctors so much better. Imagine you're learning to be a pathologist. With this data, you could put on a pair of goggles and see the world exactly through the eyes of an expert doctor. You could learn what they pay attention to and what they ignore. It's like having the ultimate teacher showing you the ropes. This data can also be used to train AI to be a doctor's helper. The AI could learn from the best human experts, and then act as a second pair of eyes. We're pointing up. Second, this research helps design better tools for doctors. Think about the software they use to view these giant images. By understanding how doctors zoom and pan, we can create more user-friendly software. Maybe the software could have a smart zoom button that automatically takes you to the most useful magnification levels. Or it could make panning across the image feel smoother and more natural. This makes the doctor's job easier and less tiring, which means they can make better decisions. And third, this goes way beyond just medicine. Think about any job where people have to find important details in a complex visual scene. Like an air traffic controller looking at a radar screen, or a security officer watching dozens of camera feeds. By understanding the visual strategies of experts in those fields, he can build smarter systems to help them. For example, a security system can learn to highlight things that an expert guard would find suspicious. This could even help with accessibility by creating tools that guide a person's attention to the most critical information on a busy screen. So how is this different from what's been done before? Well, previous datasets were built just to train AI. They had the images and the correct answers, but not the human part. This paper is special because it combines the images with the rich, detailed story of what a human expert was doing and thinking. Other studies might have just tracked the mouse cursor. But this paper shows that where your mouse isn't always where your eyes are looking. By tracking both, we get a much clearer picture. This lets us understand the type of error that was made. Was it a search error, where the doctor never even looked at the tumor? Or was it a new recognition error, where they looked right at it, but didn't realize what it was? Knowing the difference is a huge step forward. So in the end, this paper gives us an amazing new tool. It's a treasure chest of data that will help us understand human expertise, build better AI assistants, and design more helpful technology for everyone. It's a beautiful example of how computers can help us understand ourselves better. That's all the time we have for today, everyone. I hope you have fun learning with me. This is your host, ichino-ani, signing off. See you next time.